So in this chapter 24, which is what we're working on right now, the basic idea is that we want to look at what happens when you have more than one lens, right? You should have by now a pretty good idea how to proceed when you have only one optical element. Right? Either you draw the principal light rays if you want to do a sketch of it, or you do the thin lens equation for the precise calculation, right? And you have to take care of whether the image is virtual or real, object virtual or real. We'll look at that a little bit more. But this is the basic idea of lenses in combination. You're using the image of one optical element as the object of the next optical element. That's the basic idea. So in a typical setup, let's say that you have two converging lenses, one that I label here A and the other one I label it B, and you have an object somewhere here. The focal points of each lens are indicated here. These are the two focal points for A. These are the two focal points for B. Okay? So the way you start with this is that in terms of the calculation with the thin lens equation, you set up your equation for the first lens, right? So 1 over the focal length equals 1 over the distance between the object of this lens and the lens, so that I call SOA for object for lens A, plus 1 over the distance to the image for object A, right? You set up your first equation that tells you information about this lens, where the image is going to be if you know where the object is. But then there's something else that you have to do, because the light rays, after they cross at this point, they're going to encounter on their path to the observer that must be somewhere here. Those light rays are going to encounter one more obstacle, which is the second lens. So they have to go through that second lens, and that second lens is going to do something to them. If it's a converging lens, probably make them converge at some point. And that point, since there's nothing else, no other optical elements here, that will be your final image. That's what the observer here is going to see. So for the second lens, this is going to be the object of that second lens. Okay? The light rays for this lens, it doesn't matter that this is an image and not a real object. You could replace this with a real arrow, and this lens couldn't care less. Because the light rays for this lens look exactly the same as they would if they were coming out of a real object placed here. Okay? So for this lens, there is an object here. The light rays diverge some way. They're going to converge. So the equation that you set up for the second lens is your typical equation. 1 over the focal length of this guy equals 1 over the distance between the object of lens B and the lens. That distance is between this and that. You're not going to use this distance, which you might be tempted to use. That is not the distance that you want to use for lens B. Okay? The object of lens B is not that guy over there. It is the image right here. That's what the light rays that hit B are coming from. They're coming from this point. They're not coming from this point. I mean, if you go back, sure, they all came from there. But for this lens, this is where they're coming from. So that's your distance. And the other one is going to be the distance that you're looking for. If that was the question about finding the final image of that object given this system. So you have these two equations, and there has to be a relation between them, of course. Otherwise, they will just not give you any answer. So the connection is that if you have the distance, if you have calculated this distance, what am I doing here? Yeah, right. So this, suppose that you have this, so that's where the object was placed. You know the focal length of this guy, so you can calculate this number, which is this distance. Now, if you know that distance, can you find this distance? Because that's what you need in this equation. Right? The distance of the object of lens B. So if you know the distance between the lenses, that's L, then L, this whole distance minus this, is that distance. So there you have it. You have your distance to lens B, you plug it in there, you solve for the final location of the image. Right? So it's a sequential thing. You set up the equation for one lens, then you move on to the next one, making sure that you use the correct distances for the next lens. If you wanted to solve this problem using tracing the light rays, so then the same principle would apply. You go one by one, so you forget that there is something here, you focus on what's happening to the light rays coming out of the object when they cross the lens. So you will do 3 principal light rays. The one that goes parallel to the optical axis is sent towards the focal point of A. The one that goes through the center, nothing happens to that one. The light ray goes through the near focal point, turns parallel on the other side. Those 2 light rays are going to intersect at some point. That's where the image is going to be, the intermediate image of this problem. So now you have an object here. Now you can do the same thing. You can trace, you can do the principal light rays for this object, right, with respect to this lens. You can do that to locate the final image. So one of those light rays, which is actually coming from back here, is the one that is parallel to the optical axis. So that one, when it hits this lens B, is going to be sent towards the focal point of B. So that's that one. The other ones that I have, these 2 principal light rays for this lens, they don't really work for the second lens. They're not principal light rays for the second lens. They're not going to help you. So you probably want to find another light ray that does the job of a principal light ray for this lens. Okay. Now here, if this was a real object, this object will be shooting light in all directions, and one of the light rays that will be coming out will be in that direction, right? It will go through the focal point, it will hit the mirror, the lens, sorry, and it would converge, right? It would be sent towards the optical axis, and that would turn it parallel, right? That's one of the principal light rays of an object when you have a converging lens. So you can go ahead and do that, even though physically there is not a photon that coming from here going through this lens is going to suddenly go that way. That's not going to happen, but that's okay, right? The location of the image, the final location of the image, does not depend on whether you can draw one of the principal light rays or not. Okay, so you can do it, draw the principal light ray, see where the image crosses, and that's where, for example, if you wanted to see, draw the continuation of these light rays, that's where they're going to head. They're all going to hit that one point over there, which is the final image. Okay, so the message is that you don't have to be stuck with the light rays coming in from the principal light rays of one of the lenses. You don't have to be stuck with those 3, because in this case, those will not. You would not know how to bend these ones to hit that point. You can make up your own principal light ray for the second lens. It's following the rules, of course.